fifth in this series of Quantumology talks. We're looking today at the four forces of nature. So, what about the four forces of nature then? Okay, well these are they. The strong and the weak force are the ones that operate at very, very small scales. So they are operating at the quantum level, within the nucleus of the atom and in very, very small scales. So their range is limited to those very small scales. These are quite the opposite. So you've got electromagnetic field and gravity existing on a potentially infinite scale of influence right across the known universe. So they are, in effect, pairs, again, of very opposite factors within the framework of our reality. So I'm going to look at these two first. Strong force. The strong force is carried by gluons. And what it does, essentially, the strong force, is to bind the nucleus of the atom together. So the strong force holds quarks together, as we've looked at previously. It makes up the vast majority, actually, of the mass of the nucleus of the atom, because the quarks themselves make up just 1%, roughly, of that mass. The rest of it is the gluons and the quark field itself generating that mass within it. So it's pretty significant. It resists also the positive repulsion of the protons within the nucleus of the atom. So it really is doing its job, the strong force. It does a lot of stuff in this holding together. That's why it's at the top there. It's the strongest of all the four forces. The third strongest, electromagnetic being the next, but the third strongest is the weak force, which is completely different, does something completely different. The weak force essentially exists in the neutrino field, right out there in the cosmos of free radicals and everything that can happen therein. And it is carried again by a massless particle. Gluons are massless. The W and the Z particles which carry the weak force are massless. And the W and the Z do very, very different things within the scope of the weak force. W particles are charged, so they can be positively or negatively charged, but irrespective of their charge, they essentially do the same thing. They can transfer or create the transference of a proton into a neutron if they encounter it. Okay, this requires a neutrino to meet the neutron, because the neutrino are the hosts, if you like, of W particles. And when a neutrino meets the neutron, the W exchange can transform that neutron into a proton. Either charge will do this, so it doesn't matter whether it's positively or negatively charged, the W particle will do the same thing, which is quite unusual in quantum mechanics, or any branch of physics for that matter. So that's essentially what the W particle does. They are charged and they also take part in quark flavor exchange. So there's some kind of relationship between the W particle and the quark field as well. So hence this weak interaction in the quark field taking place, this crossover here. Anyway, the Z particle is, in fact, very different, because it's neutral. It has a charge of 0. There is no charge. It is a neutral particle. But what the Z particle does is it kicks things. So if the said neutrino should encounter electrons, for instance, and a neutrino encountering an electron should kind of skim it, then the Z particle that is transferred from the neutrino to the electron will kick that electron and give it extra momentum. So hence I've drawn this kind of kick line here that relates to what the Z particle does. So a very, very different kettle of fish, but both within the weak force field. Okay. Electromagnetic. Now, we're all familiar with that. You know what the electromagnetic spectrum essentially does. There it is, very, very sort of crudely illustrated from radio, which is right down here, to gamma rays, which are right up at the high frequency end. And we see around about that much of it in terms of visible light, so that's what we get. Carried by photons, which again are massless, and so it's worth noting that all these little particles at work here are bosons, all of them. Okay, so we're talking about photons, and photons do an awful lot more than just provide us with the light we can see, as the spectrum itself suggests, but they're also very active in the framework of the atom in terms of its structure, especially with regards to electrons. An electron will take on a photon in order to go up on the shell valence of the atomic structure, so it rises when it takes on an electron, and it loses an electron or dismisses an electron in order to go down towards the nucleus and bring itself towards ground state. So the movement of the electron within the atomic framework is totally reliant on photons. So they do much more than what they say on the tin. Okay, so last one on the list is gravity, and we don't know what really gravity is represented by in terms of its carrier particle. The graviton has been speculated and theorized, but we haven't seen any gravitons yet, so they're not official. We don't really know. And gravity just pulls. It pulls things towards mass, essentially. So the Earth has its own gravitational field, and its pull, which draws things to it, including us. We stand up because there's a gravitational field around the Earth. So fairly self-explanatory. When we fall over, we hurt ourselves because gravity is quite strong. It is in fact the weakest of all the four forces, but as far as we're concerned, in our reality, it's strong enough to hurt your knees if you fall over. So that's essentially what gravity does. It pulls things. Out there in the cosmos, it does a lot of other things too. There are things called gravitational waves, which are caused by shock impacts of things such as stars exploding in supernovas. They will produce gravitational waves, and there is an experiment here on Earth called LIGO, L-I-G-O, which actually studies gravitational waves and is very, very well worth looking up if you want to investigate more about those. So these are the four that are familiar. I've drawn a kind of an ellipse here to fill in some potential blanks, because there is investigation going on at the moment at CERN and at other places probably to look into a fifth force of nature, but nobody seems to be mentioning this one. I'm going to put a question mark on it because, well, we don't really know much about the Higgs field, except that the Higgs boson is a scalar boson. It's alone as a scalar boson. There is only one of its kind. And in being a scalar boson, it's responsible for scale. So if we look at scale as we know it, we look at 3D format. Things are solid, objects, and so on and so forth. They have three-dimensional shape. So therein lies our perception of scale in terms of our reality. And if you transpose that to the quantum mechanical element of what's going on, then the Higgs field, being carried by the scalar boson, is pretty important in the framework and the makeup of what we actually see. But this is just a hypothetical kind of idea, so throwing it in the mix there. There will be undoubtedly more to discover about the forces of nature than we currently know. But that, in a nutshell, is a starter for 10, if you like, on the quantum mechanical elements of the four forces. I've drawn a bit here about quarks because quarks are really quite interesting. They're being the fundamental building blocks of the atomic structure of everything that we know, are assigned colours. Scientists assign colours to quarks, and they use various other analogies in their descriptions of things because it's convenient to do so, not because quarks actually have colour. This is essential because when you're looking at a concept as complicated as quantum mechanics and as diverse in application, way beyond the reach of standard experimental facilities, then you have to have analogies that you can make sense of in your own mind. So the human brain has to be able to get around the problems presented by an invisible thing that with invisible forces, virtual particles that are massless. All of these particles are massless, and to be able to pin something that makes sense onto the picture. So quarks are assigned colour. Antiquarks, however, have no colour, so I couldn't draw any here because they are colourless. Yeah? So when you get a quark and an antiquark meeting, combining, you get something called a meson, which is a quark and an antiquark. Now, the meson is what is responsible, essentially, for being able to bind the proton and the neutron within the nucleus of the atom. Gluons bind the quarks, but mesons, still operating within the strong force, they are the ones that bind the proton and the neutron together. So when you get a quark and an antiquark meeting, combining, blending, turning into a meson, which is a very, very short-lived particle, very short-lived indeed, then you have the opportunity to explore and see how these protons and neutrons actually fuse together, because that's the particle that's doing it. So as you can see from this brief demonstration on the four forces, there's a lot more to go in terms of exploration and understanding. I hope you've enjoyed this little nutshell and that you can come back next time and have a look at the finale, because the final video will combine everything that we've covered so far in the 5 videos preceding and conclude with something of a little nutshell nugget that hopefully makes some sense. So see you next time, and thank you very much for joining me, and take care. I'll see you again soon. Bye.